Okay, kids, so we're back here and we're going to talk about accelerations in two dimensions. So this is from section 1.2 in the textbook. Now, when acceleration occurs, you remember this from your grade 11 work, there's a change in an object's velocity. And that change in an object's velocity takes a certain amount of time. And when you do the calculation, you get acceleration. Now, sometimes it's a magnitude change only. For example, if you're speeding up or slowing down in a straight line, maybe you're approaching a stop sign, you got to slow down. Usually you keep your direction the same. Or if you're going around a curve at a constant speed, maybe you're merging onto a highway and you've reached 100 kilometers an hour and you keep it at 100 kilometers an hour, but your direction changes as you merge onto the highway. Here, only the direction changes, right? Or you can have both happening at the same time. And we've talked about this as well. Maybe you're going along a curve and you're speeding up. So this is just a quick little review that acceleration involves a change in velocity, and that change takes a certain amount of time. Now, in the past, when we've talked about changing changing velocities and accelerations, it's always been in one dimension. That doesn't necessarily have to be. You can have changing velocities in two dimensions, and that's really what section 1.2 is about. So here's an example of a velocity that changes in two dimensions. It's an easy example to get us started. So what have I done here? Well, I've set up an XY Cartesian plane right here. And then I said, let's take a look at a merry-go-round with a constant speed. So picture you're the red dot and you're going around the merry-go-round at a constant speed. That means you're not speeding up, you're not slowing down, but you're definitely accelerating, because if I pick a point right here, when you're right here, your velocity would be tangential, and your velocity right here, let's say this is our starting position, would be velocity initial positive 10 meters per second x hat. And then let's say 2 seconds later, 2 seconds later, you're right here. So that's your final velocity. And here your velocity is negative 10 meters per second, y hat. First you were moving all in x, now you're moving all in y. All right? And it took 2 seconds to make that change. And you could describe your velocity at any point along the merry-go-round ride. For example, right here, as long as you draw a tangent to the circle, it's describing how fast you're going and a direction. It's describing velocity. The magnitude would always be 10 meters per second, but the direction always changes. Right here, completely in x. Right here, completely in y. Here your velocity is a little bit x component, a little bit y component. But as I said, this is our first one, so we're going to keep it simple. We're going to deal with a vector that's all x and a vector that's all y. So if you remember from our work in grade 11, here is the equation for acceleration. There's a change in velocity, and it takes a certain amount of time to do that. So let's plug in the values we know. Velocity final. What is velocity final? Here it is, negative 10 meters per second y hat. There is no x part, so the x part would be 0. It's x meters per second. It's 0 meters per second x hat, negative 10 meters per second y hat. There is your final velocity right from there. How about your initial velocity? Well, your initial velocity is all x. So it would be positive 10 meters per second x hat. There's no y to it, so it's 0 meters per second y hat. If you're wondering where I got the positive here and the negative here, well, it's because I have this Cartesian plane set up. If you take a look at the velocity for velocity initial, it's all in the positive x hat direction. If you take a look at the final velocity here, it's pointing downward. That's a negative y hat direction. And then I plug in my 2 seconds. So I do a little bit of dividing, and I get from the first bit here, I get, it's like collecting terms, right? Let's collect all the x's. So 0 minus 10 gives me negative 10, but I got to divide that by 2, so I get negative 5 meters per second squared x hat. So I brought the x's together and then I divided by 2. Negative 10 meters per second y hat, and from that you're subtracting 0 so it doesn't change. So we're left with negative 10 meters per second, but we're dividing it by 2 seconds, so we get negative 5 meters per second squared y hat. And I'm done. I just solved this problem. All right? I just solved this problem. I bring the x's together, I bring the y's together, divide by 2, and I get a final answer. And that's a perfectly legitimate way of expressing the solution to this. Now, we can draw what that looks like. See, let's see what this looks like. Okay, so you got negative 5 in the x direction, so definitely a negative x direction. Negative 5 meters per second squared y, so definitely a negative y direction. So I've drawn those two components in green here. Now, if you do vector tip to tail addition, you add those components together, and you would get the full-blown acceleration vector. There it is in red. And I've expressed it as component form here. Now, if you want to express it as angle magnitude, you know how to do this because it's 90 degrees in here. So you simply take the two sides to find the length of the hypotenuse. We know how to do that. So that would be 5 meters per second squared plus 5 meters per second squared. Square it, find the square root, and we get 7.1 meters per second squared. So that's the magnitude of this. Now, since the x part and the y part are both 5, these two sides are 5, we know that the angle theta is 45 degrees. So I could rewrite this as 7.1 meters per second squared, 45 degrees below the negative y hat direction. So I've expressed acceleration in two ways here. I've expressed acceleration in two ways. I can express it this way, right? Negative 5 meters per second squared x hat, negative 5 meters per second squared y hat, component form, or I can express the acceleration as 7.1 meters per second squared, 45 degrees below the negative y hat direction. Those two ways of expressing acceleration are completely legitimate. They're equivalent. All right, so this is our very first example of calculating acceleration in 2 dimensions. Now that example was pretty simple because one was all x component, one was all y component. It's not always like that. We're in grade 12. So let's take a look at this question. An object changes its velocity from 3.0 meters per second, 40 degrees north of east, to 2.0 meters per second, 20 degrees east of south in 1 second. Calculate the acceleration. Well, the first thing we want to do is let's take a look at these velocities graphically. So here is your velocity initial. All right, it's at 40 degrees north of east. So there's your angle, 40 degrees north of east, and it's got a magnitude of 3. So I've drawn it here in yellow. And it's got an x component, velocity initial x component, and it's got a y component, velocity initial y component. And both of these components are positive just by looking at the direction. Positive x component, positive y component. Now the velocity changes to this, 2 meters per second, 20 degrees east of south. That's your final velocity. That's what the velocity changes to. And here's what it looks like. I've drawn it in yellow. The magnitude is 2 meters per second. Here's your 20 degrees east of south right in here. And if you take a look at this, there's a y component to this. There it is. It's definitely in the negative y direction, so velocity final y component. And there's a velocity final x component, which is in the positive x direction. So that's what these two vectors look like. The object was traveling in this direction with this magnitude, 3 meters per second. And then 1 second later, it's traveling in this direction, 2 meters per second in this direction. Now, the way we really want to do this is to plug this all in to our equation for acceleration. Let's take a look at that. There it is. So here's the question again. And now I've written the acceleration equation right there. I've written the acceleration equation. So I plug in velocity final, because, right, velocity final. And from that, I'm going to subtract velocity initial. So there it is. I plug it in, and I'm going to divide by 1 second. Now, doing this in angle magnitude form Doing this in angle magnitude form would require making a diagram, a nice neat diagram, sine law perhaps, cosine law perhaps, knowing a lot of geometry and opposite angle theorems and all that. That would be pretty involved. Or you could decide, hey, I'm going to take this final velocity and I'm going to write it in component form. I'm going to take this initial velocity and I'm going to write it in component form. Wouldn't that be more convenient? Yes, it would. So let's take a look at how I got these components for each one. Let's take a look at that. So if you take a look at this here, I'm taking this initial velocity vector and I want to calculate the x component. Well, I do that. It's velocity initial x component is equal to the magnitude of the entire vector cos 40 degrees positive x hat direction. I get the positive x hat direction from the diagram, and I know it's cos 40 degrees because the x component is adjacent to 40. So I plug in all my numbers and I get positive 2.3 meters per second x hat. Similarly, I will do that for the y component. So the velocity initial y component is equal to the entire vector, its magnitude, times sine 40 degrees, because the y component is opposite the 40 degrees and it's in a positive y hat direction. So I plug things in and I get plus 1.9 meters per second y hat. Now what we're going to do is we're going to take the final velocity and convert that into component form. So look, we got final velocity x hat and final velocity x hat. Look, it's opposite to the theta. So don't think x component is always cos. Not true. You've got to draw a picture and look at it. It's a huge issue with grade 12 students. Oh, x component, I got to use cos. Not always, not always. So here's the equation for this, right? Here's the equation for this, and it's going to be in a positive x hat direction. Actually, I'll write that in later. We're just calculating the magnitude here. Look, I'm just calculating the magnitude. So I put in the full blown magnitude of the vector, 2 meters per second, times sine 20 degrees. I get 0.68 meters per second. When I draw the full blown vector, I drop the magnitude signs. I put in the positive x hat direction. Similarly, y component, if you take a look at the y component here, it's adjacent to theta, so I'm going to use cos here. So the magnitude of the y component of final velocity is the magnitude of the entire vector times cos, and that gives me an answer of 1.9 meters per second. And then when I want the full-blown vector, I drop the magnitude signs. I got to look at the diagram. Look, this direction is negative y, so I put in a negative y hat in here, and I get negative 1.9 meters per second y hat. So what have I done? What have I done here? I've broken down the two vectors into components. It's just so much easier. So I've done that. I've found these values. They're in red here. I plugged them in. What do you do next? Well, let's get all the x's together. So I combine positive 0.68 meters per second x hat, positive 2.3 meters per second x hat. I combine that, right, by subtracting. Look at this. It's positive 0.68 meters per second x hat minus positive 2.3 meters per second x hat. And that gives me negative, right, 1.62 meters per second x hat. Similarly, I've got the negative 1.9 meters per second y hat. From that, I'm going to subtract, right? I'm subtracting positive 1.9 meters per second y hat, and I get negative 3.80 meters per second y hat. And the last thing I got to do is divide by 1 second. So my final solution is negative 1.62 meters per second squared x hat, negative 3.0 meters per second squared y hat, and we're done. If you want, you can convert this to angle magnitude if you want. Pretty easy to do, right? You take a look at each bit. There's a negative 1.62 part in the x. There's a negative 3.80 in the y. Do vector tip tail addition, use Pythagoras, use tan inverse, and you can convert this to angle magnitude form if you want. Just don't know why you would convert. This is a perfectly legitimate way of writing a vector. Nothing wrong with that.